Bismillahirrahmanirrahim. So we are going to solve task 1. We are returning the function fx to Fourier series. So for question 1, we are given with this piecewise function negative 2x with the respective domain from negative 1 to 0, and then we have e to the power of x minus 1 with the respective domain which is from 0 to 1, and we have this function of x plus 2 equal to fx as our period. And for question A, we're going to sketch the function fx by using GeoGebra, and then for question B, we are going to determine the Fourier series, which is we are determining all the constants. So for question 1A, so we already sketched this graph, and we are starting with the function of f0, where we input the value of 0 inside the function, and then we will get this graph f0, the blue one, and then as we input the value of negative 1 and negative 2, we can see the graph is shifting to the left, and then as we input the value of 1, x equal to 1 and x equal to 2, we can see the graph is shifting to the right. So this is the sketch of the few period of the graph. Okay, so for question 1b, we need to determine the Fourier series fx. So we are given with this general formula for Fourier series with the period of 2 times L. So this is the generalized equation which is consists of a0 as our constant, and then we have an and bn also as a constant that we need to find. So based on the equation, we are given the domain from negative 1 to 1, so the period will be 2, and which means the half period of it will be over 2, means we divide the 2 by 2, so we'll get L equal to 1, and then substituting the L equal to 1 into this equation, so we can simplify the argument. So to find the constant a0, we will use this formula 1 over L integral from negative L to L for this function of f of x dx. So since we have a piecewise function, so we need to separate this integral from negative 1 to 0, so the function will be negative 2x, and the integral from 0 to 1 for the function of e to the power of x minus 1. So we will solve this, and we get a0 is equal to e minus 1. Okay, so to find an, so the formula will be 1 over L integral from negative L to L for this function f of x cosine n pi x over L dx. So since we have a piecewise function, we need to separate the integral into two different integrals, which is from negative 1 to 0, where the function will be negative 2x, and then from 0 to 1, which is the function will be e to the power of x minus 1. So we will get this an expression, and then to solve this integral, since we get two different function here, we need to use tabular methods. So this is the tabular method here, we can see, and then after we get the final answer, we can substitute the cosine and pi into this expression, which is negative 1 to the power of n, where n is a natural number. Since cosine is a repeating function, then we can substitute this one to make it simpler. So we will get this expression of an. Okay, then we need to proceed for bn, where the formula is 1 over L integral from negative L to L f of x sine n pi x over L dx. So same thing, we need to separate this integral into their respective limit, which is from negative 1 to 0, the function will be negative 2x, and then from 0 to 1, the function will be e to the power of x minus 1. So we will get this bn expression. So to solve this, since we have the two different functions in here, so we need to use tabular methods to solve it, and then we get this lengthy bn expression, and then after we simplify the expression, so we will get this in here. So this is the final answer for our question. So we input all the value of an, a0, and bn in here, so we'll get this expression right here. So we'll proceed with task 1, question number 2. So we are given with this piecewise function negative pi square plus x square with the respective domain, which is from negative pi to 0, and then we have pi square minus x square with the respective domain from 0 to pi. And we have this period of function x plus 2 pi equal to f of x. So same thing, for question A we need to sketch, and then for question B we need to determine the Fourier series. So for task 1, we already sketched this. So we start with G naught in here, the blue and the gray one here, and then as we input the value of -1 and -2, we can see the graph is shifting to the left, and then as we input the value of 1 and 2, we can see the graph is shifting to the right. So to proceed with task 1b, so we are given with this periodic function f of x, and with the periodicity of this function of x plus 2 pi equal to f of x, and we have this generalized expression of Fourier series. And for this function, the domain will be from -pi to pi, so the period will be 2 pi, and then the half of it will be L equal to pi. And this simplifies the trigonometry argument to nx, since the L value is equal to pi. Okay, so before we proceed with the integral, we need to check if the function is odd or even. So we input this -x inside this function, and we can see at the end we will get function of -x equal to -fx, which is, this is a odd function. So what does it mean? Basically it tells you that the a0 and an coefficient, which is correspond to the constant value, is 0. So we need to only find the bn value, and then we can integrate the integral from 0 to pi and multiply it just by 2 instead of integrating from -pi to pi. So we start with this bn formula, which is bn is equal to 2 over L from 0 to L function of f of x sine n pi x dx. So we input the function, which is pi square minus x square, inside this integral, and then the limit will be from 0 to pi. And then to solve this, since we have two different functions, we need to use this tabular method right here, and then we will get this expression. And then by inserting upper bound and lower bound, which is the upper limit and lower limit, and we will get this. So after we substitute the upper bound and lower bound into this equation, and then we will get this final expression where there is no a0 and an, since a0 and an is equal to 0. So we will get this expression of function. So lastly, task 1 question number 3. So we are given with this function f of x is equal to a square with the domain of -1 to 1, and then we have this periodicity, which is f of x, f of x plus 2 is equal to f of x. And same thing, we need to sketch and then determine the Fourier series. Okay, so this is the sketching of the graph. So we can see the first one, which is h0. So we can see the graph is start at the middle, the gray one, and then as we input the value of -1 and -2 inside this function, so we can see it shift to the left, and then as we input the value of 1 to 2, and then we can see the graph in the middle shifting to the right. So we proceed with question B. So we are given with this periodic function f of x is equal to x square, and the domain will be from -1 to 1, and the periodicity will be this f x plus 2 is equal to f of x. So we start with the general formula of Fourier series, and for this function the domain will be from -1 to 1, and the period will be 2. So the half period of it will be 1. So we can simplify this trigonometric argument cosine and sine to cosine n pi x and sine n pi x. Okay, so before we proceed, we need to check if the function of f of x is odd or even. So since we input the -x inside this function, and we will get this function of -x equal to f(x), which is an even function. So for the even function, the bn coefficient will be automatically become 0, and we need to only calculate the a0 and an. Since the function is even, we can integrate the integral from 0 to L and multiply by 2 instead of integrating from negative L to L. We start with this formula, a0 is equal to 2 over L integral from 0 to L function of x dx. So since the L value is equal to 1, we insert it here and the function will be x squared. So we evaluate this function and then we will get a0 over 2 equal to 2 over 3 over 2 equal to 1 over 3. So this is the expression for a0 over 2. And then we proceed to find the an, which is the an will be 2 over L integral from 0 to L function of x cosine n pi x over L dx. So we already know the value of L, which is L equal to 1, and then we already know the function, which is x squared. So we evaluate this integral by using the tabular method here, and we can input the upper bound and lower bound, basically upper limit and lower limit, inside this expression. And lastly, we will get this final answer for this particular question.
Okay, let's continue with my part, which is expand the function fx to even and odd function. Okay, from the given half and piecewise function, we can define the interval from 0 less than s less than 4, which means the half period is l equal to 4. Okay, next, this is the original graph that made using the GeoGebra. Okay, we can see from x equal to 0 to x equal to 2, a flat horizontal line at height y equal to 4. From x equal to 2 to x equal to 4, a parabolic curve starting at 2, 4 and curve downward ending exactly at 4, 0. This original curve serves as a right-hand side foundation for both even and odd extension for our next calculation. Okay, first let's do cosine series, which is even extension. Okay, why it was even extension? Because function f negative s is equal to function fx. Okay, from that, we have a Fourier cosine series formula, which is given here. Okay, from the formula, we can see there is two unknown, which is a0 and also an. Here, we need to determine the unknown and we need to find it, which is calculate both unknown to solve the formula. Next, even extension graph. To expand a function into a cosine series, the function must be extended as an even function over the interval given before in the question, which is negative 4 and 4. Even functions are symmetric with respect to the y-axis, as defined f negative s equal to fx. Okay, for the mathematical piecewise definition for the even function, I put it below, which is the input for the GeoGebra graph. Before this, I used the original function for the original graph, and I put the piecewise definition for the even extension, and the graph is shown as I put here. Okay, for the left side, which is from negative 4 to 0, a parabolic curve starting at negative 4, 0 that rises up to negative 2, 4, followed by the flat horizontal line from x equal to negative 2 to x equal to 4 at y equal to 4. Okay, for the right side, from 0 to 4, a flat horizontal line from x equal to negative x to x equal to 2. This is at y equal to 4, and it followed by the parabolic curve dropping from 2, 4 down to 4, 0. This graph will look perfectly symmetrical across the vertical y-axis, and it's the same as a mirror reflection. Okay, first, to solve the cosine series, first let's find the first unknown, which is a0. Okay, the formula for a0 is given as shown here. To solve it, we can just substitute and integrate it as usual, because for this integration we doesn't need to use the integration by part. Okay, the answer is 16 over 3, and we can summarize it, but we will do that later. Next, let's find for the second unknown. For the second unknown is an, and the formula also given. Let's substitute it first. Okay. After the substitution, there is divide into two parts. So the first part we can integrate it as usual, but for the second part we need to use the integration by part. So we need to evaluate it separately. For the first part is done and as shown here. Next, let's continue for the second part. For the second part, okay, as I said, we need to use the integration by part. So I use the tabular method, and for the answer is, let's continue for the next step. From the tabular method, we got here. So next, let's continue for the next step, which is solve the integration. Okay, now we can solve the integration for the second part. Okay, first we solve for the upper limit, which is x equal to 4, and the answer is we got 0. Okay, for the lower limit, x equal to 2, and after substitution we got this answer. Okay, next let's solve it, and we got for the answer for the second part. Now after we got the first part and second part, we can solve for the unknown, which is an, and we got the answer. Now since all the unknown is calculated, we can solve for the cosine series, and this is the answer for the Fourier cosine series after we substitute a0 and also an. Okay, let's continue. Okay, next for the sine series. Sine series is a odd extension, which means f negative s equal to negative fs. So from that we got a0 equal to 0 and an equal to 0. Also for the Fourier sine series formula is given here, and the unknown is bn. Since we already determined the unknown, we can find it. Okay, before that, this is the odd extension graph. For the mathematical piecewise definition for the odd extension is shown below, and the upper is original and the lower is the odd extension. To expand the function into a sine series, the function must be extended as a odd function over the interval -4 and 4. Odd functions are symmetric with respect to the origin. As I said, f negative s equal to negative fx. So for the graph, the left side is from -4 to 0, a parabolic curve started at -4, 0 that curved downward to -2, -4, followed by the flat horizontal line at y equal to -4 from s equal to -2 to s equal to 0. For the right side, from 0 to 4, a flat horizontal line at y equal to 4 from x equal to 0 to x equal to 2, and it followed by a parabolic curve dropping from 2, 4 down to 4, 0. The graph will display a rotational symmetry of 180 degrees around the origin graph. To find the bn, the formula is given as here, and we can substitute it as usual. But after the substitution, we got two parts, which the first part we can solve it as usual, but for the second part we need to evaluate it separately, since we need to use the table integration by part. Okay, for the second part, since we need to use the integration by part, I choose to use the tabular method. From the tabular method, we got here. So next, let's continue for the next step, which is solve the integration. To solve the integration for the second part, first we solve for the upper limit x equal to 4. Next, solve the lower limit x equal to 2. Next, let's solve for the second part. Okay, since we already solved for the second part, we can solve for the bn. and we just need to substitute for the first part and also for the second part, since we already solved it and we got the Bn. Since the unknown is calculated, we can solve for the sine series. After substitute the Bn calculated, we got the Fourier sine series, and that solve it for the task 2. We continue for the task 3.
Alright, now on to the third question, which is regarding harmonic analysis. So the data given for the x and fx value, and the question wants us to find the Fourier series expansion up to the third harmonic. Okay, now for the first step, we need to find the summation of y cos nx and y sin nx. By using the given data and put it in Excel, we can easily find the summation of the given value and then the value of y cos nx and y sin nx. We need to find for each x, which is the first one, y cos x and y sin x, y cos 2x and y sin 2x, and lastly y cos 3x and y sin 3x, because the question wants us to find up to 3 harmonic analysis. Next is to find the n-root value. To find the n-root value, we use the formula 1/6 times the summation of fx, and then we already get the summation of fx. We just substitute into the formula, and then get the n-root value is 1.03. Next, for the a1 and b1, for a1 we use the fx 1/6 times summation of fx cos xr, and we get the answer is 0.2025. And for b1 we use the 1/6 times summation of fx sin xr, and then we get the value is 0.1895. Okay, next we need to find for a2 b2 and a3 b3. So for the formula is almost the same, but the value of x is changed. For a2 and b2 we use for 2x, and for a3 and b3 we use for 3x. So the value for a2 we got negative 2.067, and for b2 we got negative 1.1835. For a3 we got negative 0.533, and for b3 is equals to 0.4. To find the harmonic analysis, first we need to find the C0 value. The C0 value is equals to 1/2 times with N0 value, and then we got the answer is C0 equals to 0.52. Okay, for the first harmonic, we need to find the alpha 1. Alpha 1 is equals to tan inverse A1 over B1, and then we got the answer is alpha 1 equals to 46.9. For the C1, we need to find by using the formula square root A1 square plus B1 square. And then we substitute the value, and then we got C1 is equals to 0.28. Alright, now we need to find for the second and third harmonic. For the second harmonic, we need to find the alpha 2 and C2. Same with the first formula, but instead of using A1 and B1, we use A2 and B2. Okay, for the alpha 1, we got the answer is 60.21. For C2 is equals to 2.38. For the third harmonic, alpha 3 is equals to negative 53.11, and for C3 is equals to 0.67. Lastly, we put all the value that we already calculated into the formula, which is C0 plus C1 sin x plus alpha 1 plus C2 sin 2x plus alpha 2 plus C3 sin 3x plus alpha 3, and then we got the answer for Fourier expansion series, which is equals to 0.52 plus 0.28 sin x plus 46.82 plus 2.38 sin 2x plus 60.21 plus 0.67 sin 3x minus 53.11.